today on the bench I've got this Fluke 702 documenting process calibrator. This is a really cool piece of equipment that needs repair. At the moment it doesn't turn on. So we're going to have to debug that and find out what the issue is. And I'm really excited about repairing this piece of equipment because it's a really cool toy. It basically has some multimeter-like functionality. You can use it to measure volts and resistances and current. But what's really nice about it is that it can actually source voltage and current as well. So you can use this to actually calibrate pieces of equipment that both output and take in current or voltage sources. Normally this thing, they say a documenting process calibrator, is used to calibrate pieces of equipment on process plants, so like chemical plants and so on, where they measure, say, pressure. They have a pressure transducer or a temperature transducer. And the normal way that those things work is they output a current signal, which is why current's so important on this. So you can simulate, say, a pressure transducer by outputting current through this into your controller, into your process controller. And at the same time, you can power your transducer via this. So this actually has the ability to provide power, measurement power, to a device, and then you can actually read back the current from it, the current signal, and get what that is. There's quite a bit that's actually designed around process calibration here. So for example, we've got a little thermocouple port here, so you can do direct measurements of thermocouples. You can also simulate thermocouples, and then on the side over here, there's this little kind of jack down here that takes some additional, I actually don't know what the jack's called, it's got a weird symbol, but you can put pressure transducers in here and actually measure pressure as well. Now, the signal path did a teardown repair of the follow-on version of this meter, so the 744. And in that teardown, it was a great one. It had a similar issue, it wouldn't boot up. I'm hoping mine's nowhere near as complicated as that. But because he had, I think, a firmware issue, and that might be that'll be very tricky to track down. But what's really nice in that video is he showed that there is a schematic for this, and indeed XDevs has the schematic and the service manual and everything else for this. So I've got no excuse. Apart from missing firmware, I should be able to repair this, right? Or maybe a bad, as long as the Fluke branded ICs that are in here is primarily the ADC, as long as that's still good, then I should be able to get this to work. So given it's a power issue, I did look at the manual a little bit about the power, and I learned some interesting things. First of all, this thing has a battery, right, which I've taken out already. Oh, it came also, right, look at this. I bought this on eBay for £80, and it came with this beautiful bag. I mean, it's not that beautiful, but it's so nice to have these kind of things all together. So it came with this bag, a few kind of like, loop back cables. It also came with these really nice Fluke probes, the kind that actually has a banana jack as well as a tip. So what a cool, like, find for the 80 quid to get the probes and the bag as well. I mean, that alone is starting to look like good value to me. It also, so the battery's here, but just talking about the power, this power unit will not charge inside this meter. So even if you plug this thing in, it will not charge this battery. So we're gonna have to figure something out for how we can charge this battery. Okay, so how else can we get power in? Well, we can get power in through this jack here, and I do have the power adapter for that. So again, what a deal, right? To actually get one of these rare kind of Fluke power adapters as well, all in there for £80. Well, that's great. So supposedly this meter will start running purely off AC supply. It will not charge this battery. I'm not sure if it still needs a battery inside there to be able to run. So we're going to do some digging and have a look at what's going on inside here and try and figure out what's going on. I did look at the service manual, and I noticed in the schematic there's also a backup battery in here. And I noticed that backup battery has something to do with the power on circuit. So I'm going to do two things. First of all, I'm going to check that this supply works, and put it on a DC load and just check that it reaches its rated 870 milliamps at 7.5 volts. So I'll check that that's good. If that's good, then I know that this thing isn't starting up due to some internal error, and I'll start tackling that. So you can see I'm getting 7.6 volts here. That's great. And I'm going to set the current limit to 80 milliamps. Let's turn this on. And I'm getting 6 watts, 7.5 volts and 8 amps. And that looks great, right? So I'm not getting any magic smoke. So I'm pretty happy that this power supply is just fine. And that I know that this outer connector is positive. So what I'm going to do now is get an equivalent one of these connectors. And I'm actually going to run the meter off my bench supply so I can check what its power draw is and see if it's actually doing anything when I press the power button. Okay, so my bench supply is set for 7.5 volts. I've got something that will make contact but not sit in there, so let's give that a try. So let's just see what happens when I first insert the jack. Okay, I see nothing. I'm pretty sure that there is something dead in here, and given that there was absolutely no draw here, I would have expected, you know, 1 or 2 milliamps at the very least, or 10 milliamps, just as it kind of, you know, the startup circuitry turns on or everything else like that. But it looks like absolutely nothing's coming on. I'm looking at the schematic. It might be because the battery's dead inside here. So I'm going to open this up. We're going to take a look inside. I'm going to check that internal battery first and see where we go from there. I'm going to open this up. It looks like it's just 6 screws at the back. It's like TX15s. So they're not captive screws. So let's get them out and save them now before I lose them. So in the case you can see there's a little bit of sponge here. That still looks pretty good even after all this time, because this is not a young board. 95. Nice. Now the way I think this opens up is sort of like a concertina. Okay, so we have our input board, our power input board, but then that comes along over this board connector to the main power board, power supply assembly, and then, oh yeah, look at that, beautiful. Okay, so that concertinas, oh come on, how nice is this? Oh, wait, does that all just cleanly come off? No, it doesn't come off, okay, but does it lay out? Oh, okay, I'm in love. Look at that thing. How beautiful is that? I mean, the fact that it's so complicated and yet actually concertinas out perfectly so that I can actually work on all of the boards while it's fully assembled. That is amazing. Right, what to do? Well, I'm pretty sure there's a battery in here somewhere. So let's have a look for that. I'm just going to pop this back in here for a moment, and we will flip these boards back over. So I think I'm just going to undo these clips here, here, and here, and here, and I think this display might come off. Let's see if we can get rid of this display module. Have we shed the display module? Oh, and there it is. Come on, look how beautifully made this is. Okay, I've got some kind of port here. Did I disconnect something accidentally? No, but look at that. Look how beautiful this is. Okay, so we've found our battery backup. So I am going to pop this out. And I'm seeing 61 millivolts. Oh, I think that's definitely dead. Do you reckon it's this simple? Do you reckon I just have to replace this battery? That would be a nice one. Let me just get another one. Let's give it a whirl. Okay, that's in. And I've got to try it, haven't I? Okay, nothing. Too easy, hey? Too easy. I think in the first instance, I'm going to buzz out this, where this voltage is going. I think I can probably locate a test point off the schematic somewhere here that will actually give me the, you know, check that this voltage is getting through to here. Okay, something's not adding up here. This is the schematic for this board here. I mean, they don't agree. Right, this board should just be a damn straight through board. Instead, I have something far more complex. You'll notice that the board is Fluke 700-1004B, and this is Fluke 700-3034 Rev B. It's true, the service manual says later versions have much more increased specs, and they say also that the 702, which is the top of line model, has a lot more kind of going on inside of it. So yeah, the one thing I could deduce from this that's kind of interesting is if you have a look, the battery AC plus and AC common, they're actually connected together at the jack, and when the barrel jack's inserted, it actually disconnects the battery plus from the AC plus. So it looks like the battery gets fully disconnected when the AC adapter's in, because I was looking for where these connections were on the other schematic, but they're not there. So this was the first of many dead ends that I went down. My thought process was just to follow the power supply as it goes through this first PCB, which turned out to be fine, and then see where it went inside the main power supply PCB, because there's a switch mode converter on there, and I thought maybe that would be at fault. But as you might have guessed, that loose cable we spotted earlier is actually the problem. So we'll just skip forward to that. It's a little alarming. Was like that before? I'm gonna have to rewind the video, but this connector's off. I didn't take it off. It might have come off, but this connector's pushed on the wrong row of pins. I'm wondering if someone's been in here before me. Oh my god. It's in French, but it's working. This connector wasn't lined up, and this battery was dead. Well, we won something today. Right, I'm going to turn this off. I'm going to put this back together. Unless you guys want to see anything. I'll tell you what, guys, we've come this far. Let's take the power off, and let's have a little look underneath this shield. Because we may as well have a look at what's inside here while we're in here. Yeah, let's just have a look inside here, but I'm super happy with that. I mean, that's such an easy fix. But, I mean, was that me? I'm going to have to check the video. Did I couldn't have done that, right? I mean, the only thing I've done to this thing is change the battery. Well, I'll tell you what we'll do. We'll use my my multimeter to actually check the calibration on this. But I'll point out a few nice things. So this is such a lovely idea, right? Isn't it? You can use a bit of Oh, look at all this. That does not look good. It is right near the input connector though, so I wonder if that's smoke. Oh, you know what? That does not look good. So we'll check that out later. We'll actually do a performance check on this. But it's a really nice idea, right? To print a PCB that you then use as a shield. I mean, such a nice way of kind of screening electronics, because you could probably, whip this up in KiCad or whatever it is quite easily. Really like that idea. Never thought about that before. Okay, so we can see a few things down here. There's the Fluke branded chip here. That's probably the multi-slope converter, so the ADC. We've got a Motorola up here. That'll be the brains of the system. And then I've got Intel and Flash up here as well. So that's your high and your low Flash. And then I've got a Maxim part. Oh man, no, we have got some damage. Wow, okay, that's crispy. Oh no, okay, there's some real serious issues here. So yeah, look at that. That is a dead transistor. And these are totally smoked, these connectors. That looks challenging. These are the source voltage ports. And they are blown to pieces. Jesus. The smoke kind of comes up here, but I wonder if that's just smoke. So bad news upon more bad news. So if I have a look at the back of this main PCB, I can see that there was another resistor that's died here, but what makes this even worse is it's clear that the trace has been cut or has failed underneath that leg. So not only has a resistor blown up, that resistor looked like it was a bodge resistor. Either somebody deliberately cut that trace to then insert this resistor, and so it was done at factory, or somebody was trying to repair this. And I don't know, I'd like to believe that Fluke does better soldering than that when they're doing their bodges, because that's a pretty awful ball of solder right there. And we could see some of their Fluke branded bodges if we have a look over here, right? So this is what Fluke does, and okay, that's a lifted leg, but generally speaking, pretty neat apart from that lifted leg. Yeah, pretty neat bit of bodging. So I don't think it was them. So right now we're looking at this guy blown up, CR107, possibly one of these double diode packages. We're looking at two inductors blown up here. They are probably the 100 nanohenry ones on the two input jacks, and definitely a dead resistor on that relay. But what I will do is do a functionality test. I'll just see what's working right now in the state it's in. I've just kind of loosely put it together. I'm amazed those boards don't short out. And at first I was like, oh, what brilliant design to make, boards that would sandwich but not short out with each other. But I'm wondering if whoever was in here before me just removed any insulating material that was in there. Anyway, the machine starts up. I'm just going to turn off that for a second. If I go to setup, I can then go to choices, previous page, and the first fix I could do was change this to English. So, that was another repair I did. Then there's the temperature scale here, IDS 90. It's really nice that you can actually choose the temperature scale, the definition of the temperature scale. That shows that this is really something thinking about calibration here. It currently thinks it's 1957 though, so we'll have to calibrate that as well. What's kind of cool is, we'll choose that. I can have a look at the calibration dates, and you can see this thing was last calibrated in 97, but it has calibration dates for each functionality and the ability to calibrate them. So if I hit calibrate, I apply a short and I can go through the calibration thing. So what a nice piece of equipment. I really want this thing to work. So I'm pretty keen about getting this source measure working. Let's try putting a 1 volt source on. Okay, I'm pretty happy with that. I'm not sure why the 0 is the way it is, but look at that. 1.0001, 1.0001. Okay, I am very, very, very relieved the ADC is okay. That would have been impossible to repair. Okay, so that works. We could just try another range. We'll go to 10 volts, okay. Beautiful, 10 volts works. So it was about this point that actually the wheels fell off. I tried to test higher voltage ranges, had a little bit of issues there. Then I moved on to checking that the current measurement worked. That didn't work. We just kind of capped out at 97 milliamps, and no matter what I was putting through there. Then I tried to do resistance measurement, which you can also do on those ports as well. It's also the current sourcing ports, and that didn't work. You can see I got no measurement at all, so something weird is happening there. And then also the same goes for, when I tried to measure resistance itself, but I was getting very odd, unreliable readings. Finally, the last thing I checked out was the voltage sourcing, and you could see that the values I was getting were jammed out at 29 volts. So clearly it had no control over its voltage output or its current sourcing, and it needs both of those for the resistance measurement to work. So something's clearly wrong here, and I needed to take a look at that burn section once again. So the front end seems to have seen some damage. One of the things you can see just looking under the scope right now is this package here is a blown transistor. It's not actually a transistor. CR stands for I think common rectifier or rectifier. So this is actually a double diode package, back-to-back diodes essentially going from this leg to the central one and the central one back to here. And this is usually used as kind of input protection, rectification, that kind of thing. That's popped. And then there's a few other issues as well, like that you can see. So I've actually done a little bit of desoldering over here, but what you could see is that I removed the plastic shrouding around one of the input terminals. Essentially, I just heated it up and then could slide the plastic up. I heated it up with my soldering iron and then could slide the plastic off. But you could see quite clearly that the copper traces literally burnt off the board. Here I had a pair of capacitors and an inductor that are gone. That I desoldered them, but they were kind of a little bit blown as well. Yeah, but perhaps the first problem is literally the traces for my inputs are completely gone. I think there was one originally underneath this silicon pad to here as well. Yeah, so that's popped. If we move up a little bit, we'll see a pair of diodes here. Then we see these two packages here, and these are MOSFETs, right? So I think these are the output MOSFETs. Just to the side of them, you can see some more packages. These are two AVs. I think they are actually transistors that are used to drive the gates of these MOSFETs, or they could be, I think they call them like a fallback current limiter. So essentially they're there to just limit the current through these MOSFETs in case of an output short. One of those is gone. I think this upper one here looks like it's testing as a dead short across its terminals. So whatever it is, it shouldn't be a dead short there. And what else did we see that was a problem? Oh yeah, one of these MOSFETs is testing as a dead short. One of these is testing as an open, rather in diode mode. So I'm pretty sure that one of these is gone as well. The other issue that we have is on the other side of the PCB. So you can see that on this relay here, right, so this upper relay on the board, I have this kind of remnants of what was once a resistor. And this is where things get a little bit confusing. So this comes into what looks like a double diode package, another one of these A7 Zs, right? So I think this is one of these back-to-back double diode packages. But it's a little bit strange for that to be there because it's not on the schematic, right? Or at least not on the version that I have. A TP45 is actually to do with the driving of the MOSFETs. So it seems that somehow the output directly comes into the driving area of the MOSFET. So a little bit strange that is, to be perfectly honest. So I think we're in a bit of trouble with restoring this because we're going to have to essentially rewire this entire front end from the output terminals all the way to the driving MOSFETs and everything else. So what we'll do is we'll look at the schematic a little bit more, try and understand the schematic, and then talk about how we could perhaps rebuild this. Because even though these traces are gone and the via is kind of lost as well, and I have no idea what this pad was for. It looks like there was perhaps a capacitor here as well, but that was missing. That was missing when I got here, right? So I'm going to have to... Yeah, okay, so what I'm going to have to do is I'm probably going to have to desolder these input relays, and then actually try and look at the schematic markings. Also remove this plastic shroud and this silicon kind of sleeve down the bottom, so I could see all the PCB markings. And then I can actually try and figure out if there was a capacitor here and it was removed by the previous guy. And also like which of these is capacitors, which of these are inductors. And yeah, I'm not too worried because provided I can figure out the current path that blew all of these things up, then I can replace the parts on that and rebuild that section. I'm fairly sure it went up through these drive transistors and killed one of them. I'm kind of hopeful that didn't cascade fail through everything, but it could have cascaded through. You know, I could have blown these diodes, and then once those were blown, the next component to fail is the MOSFET blows, and then, you know, because that's an open short, maybe it kills the voltage rail, or through that rail, you know, goes into some of the driving circuitry and kills the DAC, say, for example. That would be an absolute nightmare. Not totally unsolvable, but basically I'd be rebuilding this entire thing from scratch at that point, and then I probably would give up. So what we're going to try and do, is rebuild this front end. So we need to look at the schematic to try and figure that out a little bit better. Okay, I'm going to show you why I think this section up here has got bad MOSFETs and so on. I've got my meter in diode mode, and essentially if I just kind of bridge these out, I'm going to read 0 volts. and that's because there's no diode junction in there. But if I kind of like come along and pick something like this diode, sorry, this transistor here, just put 2 legs on it, you can see I get 1 volt. Well, that's fairly high. If I kind of flip around to this guy, I get an overload. If I flip them around, I still get an overload. Okay, so I've started to think that that diode there is probably out, because I'm not seeing what I expect. I expect to see about half a volt on that. If I go to the package that's right next to it, that I think is absolutely equivalent, yeah, I see 1.69 here, so that's a double diode drop. If I switch that side, I see 0.64. If I switch this, I see 0.64. So that's behaving like what I expect it to be, which is a transistor looks like a set of diodes, right? One of the things I expect to see though is on these MOSFETs, which are these 3-pin packages here, what you typically see is, you can see this resistor, that's a resistor going onto the gate. So the gate's going to be high impedance from everything, right? So if I put this here, I get a short from the gate to here. I actually get a short across all terminals, right? So that's definitely not what I expect. So what do I expect to see on a MOSFET? Well, on a MOSFET, I expect to see a body diode, right? So that's what we're seeing here, from here to here. And so that means in the other way, I kind of expect to see high impedance. So with those components identified as bad, I started to look at other components, and I noticed that the relays were covering up a lot of the traces that I needed to check were okay. So I started desoldering them, as you see here, and that actually led me to find that one of the relays was bad as well. So we'll take a look at that now. So the relays in this Fluke are actually pretty interesting. They're these TN2E L2 5E relays. The TN2 is the form factor, and this is quite a compact form factor. Normally relays have a spacing between the pins that sort of keys them, whereas this has a regular 2.54 millimeter spacing all the way around. They're also, what's interesting about this relay is it's a double latching relay. And what do I mean by latching? Well, if you put current through this, the 2 outer pins, then you'll actually the relay will latch to one state and actually short out 2 of these pins. But if you then remove the current, it remains latched in that position. And if you put the opposite current through those 2 pins, it will actually latch the other way. It will tick over to the other side and then short those 2 pins out instead. So that's what that L2 means in the name. And then the 5V is just that you need a 5 volt. 5 volts is the normal activation voltage to actually kind of get these things to latch over. They actually latch at some lower voltage, like 3 volts, but 5 volts, you essentially need 5 volt logics or 5 volt power logic to actually control these. Now this is one of the relays that I pulled out. You can tell it's still got some of the scorch marks on the side. You can see some of the soot that's on there, but otherwise it looks okay. So that was up there, but the relay that was in the lower position was actually a little bit more damaged, and you can see the damage just here. So I'm going to try and zoom in on it, but yeah, you can see that the actual plastic inside this relay is melted up into the fingers of this kind of latching side, and it was quite hard to remove this relay because these pins here had become a little bit bent or a little bit loose inside the relay itself. So this cracking here, I mean, I desoldered this myself, but this cracking wasn't my desoldering, I don't think. I think it was actually that because this thing's weakened, because it supported, I think, mains current, basically, or something of the order of mains current over these 2 pins. So, yeah, I'm dancing around outside the zoom level. So I needed to find replacements for these. Fortunately for me, I couldn't find anything in a similar series. These relays are no longer produced. There's no equivalent that you can get, but I did find an eBay seller who sold me 10 or 20 of these recovered from military equipment. I have actually got a ton of these relays now. I'm really quite happy with it, and they all look in excellent condition. They need a little bit of cleaning up. I need to remove some of the kind of excess solder left on from their recovery so that they'll actually fit through the pins first time. And I am going to check them as well to make sure that they are fully operational. But it looks like I can replace these relays, and I'm going to replace both. It's likely that whatever these recovered relays went through was a lot more gentle than what these relays have been supporting possibly dealing with mains electricity kind of going right through them. So I've been doing quite a lot of work to figure out the schematic here. And I say figure out the schematic because I do have this schematic. This is the most important page for me at the moment in the manual. And it does have almost everything in here. But what I've noticed is there's a little bit of differences. So I've been looking at images of the boards. I've overlaid the front and back images so that I can help try and track traces down. And I've been working with them kind of half opaque to just try and see exactly what's going on here. And it's quite a compact layout in certain key parts, so it's quite hard to figure out exactly what's wired to what without doing this. And then I've even kind of rebuilt this schematic in KiCad and then actually laid out the parts so that I can actually compare them, So, for example, these two diodes here are these two diodes. These two transistors are the MOSFETs here and here. And then these are the driving transistors on the gates of those MOSFETs. Now, I've had to do all this because the schematic that's provided isn't quite right, especially for this front end part here. And that's the bit that's got loads of blown up parts. And one of the things you'll notice is this U133 is actually the driving output op amp. It connects through to the posts over here. Let me just try and highlight that. So this is the source high and the source low posts here. And this driving op amp actually connects to the high side. It either goes directly through here like this, or it can couple up through this relay. It can go into this relay here and then couple down into this way. Anyway, so this is the driving op amp for the high side. You can see the configuration that they have on the schematic is that it somehow couples through these the base of this transistor that's then going through this MOSFET that's pulling high, or this it's a push-pull configuration, so you've got a pull low. And it seems that this op-amp is actually driving it this way. But interestingly, in the version I have, the op-amp is directly on the output. And these MOSFETs and these transistors seem to be actually acting entirely just as a current limiter on the input voltages of that op-amp. Okay, so they're not actually directly in the signal path like it appears in here. So something to watch out for. It really took a long time because I thought I had a short or some break that was meaning that I was missing something here, in trying to find agreement. But I am 99.9% certain of these connections because you can see a lot of these traces. And, the fact that this diode then goes into the op-amp's power supply, and this one too, is you can't deny that it is on the top layer of the PCB. It's easily visible. It just didn't make sense, especially when you look here that actually this has separate supplies, and that these diodes, the equivalents of these ones here, CR104 and 103, they are actually on the output here, whereas now they're on the power supply. At least in reality, they're on the power supply of this op amp. Very strange. Anyway, what I thought I'd do, I'm going to share these images and the KiCad schematic as well in the description of the video. But what I thought would be interesting for everyone is just to kind of go over this schematic and talk about how all of the functionality they've got, how they achieve some of the kind of amazing kind of precision that they have here. Because, for example, they claim that they have an effective 24 bits of resolution for output and the voltage, which is really impressive, right? That's very high precision. So we'll talk about how they do that. Plus, there's some interesting functionality. Not only does it source voltage, it sources resistance. So it has to somehow accurately generate that. And that's kind of an interesting story. So we'll kind of go over it. What you notice is we have this, starting at the input, we have this K1, and what K1 can do is it can redirect the inputs being from the source high and source low jacks to actually being the thermocouple jacks. And so you can see that this system actually provides a lot of functionality in your system. Although you've got multiple jacks on the front, in fact they all kind of come down to just two basic functionalities, which is source resistance and voltage, or source current jacks. We have some input filtering. There's an inductor here, L13 and L14. In fact, there is inductors here as well, and there's an inductor here as well that's just not on the schematic, but it's on the board. And then we have a few bits of information, right? One of them is this low side here actually comes into this op-amp, which buffers it and actually sends it out to something called the summing node. And the summing node is actually up here, and it's the other side of this driving op-amp. Now that summing node's really key. It's where all of a lot of signals come together or added together to actually control the output. At the same time, you have this other side here, which is your reference voltage, okay, for the comparison of this op-amp. And it's this reference voltage that's here that's the high precision 24-bit. Up here, this other voltage seems to take into account everything else. For example, the offset of the source low, which is coming from this point here, but also square wave, generation. So you can actually output a frequency on these terminals as well, with controlled amplitude, and that's done via this upper line here and this summing node. Some cool things to note about that. The summing node traces are all heavier, and that's because they're actually guarded. And you can understand why that is, because they're actually behind some pretty high impedances. So the voltages that are driving this summing node are actually behind very high resistances to make sure that the current flow doesn't actually, you don't end up forming dividers with the inputs, okay? They're not, for example, the output of this op-amp is, low impedance, but because it goes through this 412 kilo ohm resistor, it's not going to affect, say, the value of source fine, because they're separated by 800 kilo ohms of resistance. So because this line is driven very weakly, you have to guard it from interference, and also you don't want kind of leakage currents as well. So they actually have an op-amp here driving a guard trace around the outside of all of those traces. And it also means that these traces are all very close together. So they're actually, if I just kind of scroll up, this is the output amplifier, but this amplifier up here is the one that's actually doing all of the summing as well. So this is our driving, which amplifier is that? So this U133, in fact, is this guy here, whereas we have an output buffer stage, which is U4 now in our schematic. So the guards for this, you can see one of the guard traces just kind of around the pin up here. Let's try and draw. Okay, yeah, so you can see a guard trace just around that pin there. That's one of the examples of the guard trace. What we've got, some interesting kind of op-amps here. This is an op-amp that is entirely AC coupled. So you can see there's capacitors here. And weirdly, like the input and the output are AC coupled onto this line, onto the summing node. And what that is that's a 3-pole filter. And that's filtering out PWM noise on this line. That's the actual way that they generate the precision voltage. So how do they actually generate that? Well, actually, our voltage reference for this entire system is in fact this bit here. So we have a precision, I think 7 volts reference here coming off this 10 volts line, and then it is divided down to about 1.4 volts. That voltage then comes up here to one of the many FET switches that we have in the system. And what you can see is if ohms is on, if this ohm on line is high, then this is actually connected through. Now that's a bit weird, but essentially when we're doing source resistance, then actually this is open and this one is closed. Okay, so I think it's meant to be the other way around. Okay, so what does that mean? Well, when we're actually just sourcing voltage, our voltage reference for our entire system is this voltage reference that you see down here. But if we're sourcing resistance, then our entire voltage reference is actually taken from over here. And so what do we see over here? Well, what we see over here is a accurate 10 ppm, 121 ohm resistor. And that's actually our sense resistor, our current sense resistor. So our low terminals come in here along this way, and then pass our low current would pass through this resistor that you see here. This whole setup of op-amps that you see down here, its job is to provide a virtual ground at this point for that current, so actually to sink that current away. But by doing that, we actually can then measure the current that's being applied to these jacks, and then we can use the generated voltage at this side as our reference, so that we can generate a corresponding voltage difference across our posts that corresponds to a known resistance or a set resistance. So, if we've got some device, say a multimeter attached to our source jacks, and it's providing a current in order to measure resistance, we can measure what that current is and then provide an opposing voltage corresponding to the resistance that we want it to think is there. Okay, so it's quite a clever idea. Instead of using your precision voltage reference, you actually use a current developed by a voltage developed by a current shunt as your reference instead, thereby allowing you to do a source resistance. Now that whatever voltage reference we have, whether it's that current shunt or that precision voltage reference, it comes through here, and here what we seem to have is a 10 times multiply. So to give us access to different voltage ranges, voltage or resistance ranges. There's a 10 times multiply for that. Then that passes up here and it goes into two areas. One of the areas it goes to is this max 543. That's I think an 8-bit DAC, or maybe a 12-bit DAC, and that is I think used only for square wave or frequency generation. So it's used as amplitude control when you're trying to output a square wave on these jacks. And that's what this line sort of all corresponds to here. You've got this frequency coming into these kind of switching gates that control these FETs, and then you've got the square wave on. So if square wave on is on, then these NAND gates are enabled, and then when this frequency line is toggled, essentially this set voltage is actually toggled off and on into the summing node, giving you your square wave, right? This is what we call a multiplying DAC. So actually it outputs a current, not a voltage, that's some multiple of the reference voltage that's being supplied to it. Anyway, because this outputs a current, you actually need a transimpedance amplifier to convert that to a voltage, and that's what you have here. So where does the precision voltage control come from, right? This is obviously a low, 8, 12-bit DAC. I can't remember exactly which one. And yet we're saying we get 24 bits of resolution on the voltage control. Well, that comes through these guys here. So what you can see is source PWM. And what we're doing here is we're switching in either a ground or this voltage reference into this line here. And so we use PWM control to switch this precision reference in. And using PWM control, if you've got a high enough frequency, I think the frequency here is 1 megahertz perhaps, something like that. Oh no, sorry, it's a 1 kilohertz PWM. But if you do very precise timing control on that, then you can actually get very precise voltages. And you're really only limited by how high you can get that PWM frequency and how much smoothing you do. So what kind of time constant you set for your loop to get a precision voltage out of that. It means that you have very low bandwidth, right? But we're not trying to do high bandwidth things here, right? If we're doing frequency synthesis, that's done up here, and it's outside of this line here that we do the actual kind of precision voltage control. What you can see here is we've got some additional PWM control here, a 10 times divider. I'm not really, I think this is just again to get you into your range. So it's a division. We've got a 10 times division here. I'm kind of surprised it says 10 times because this looks like a 1 to 5 division. So because you've got 2K versus 10K in this precision resistor pair here, but whatever, I'm not sure what's going on there. Anyway, this PWM needs to be filtered out, and that's the job of this 3-pole filter that you see attached here. And that's everything, right? About the only thing that's kind of left is this output stage, but we've gone into that. There seems to be some high side feedback as well coming along here, and then going through a divider, or if it's not this divider, it actually instead comes through here. So you've got a choice of division. That seems to be controlled by RNG1V. I actually don't know what that is. And then up here we have a source fine again that kind of couples into here. That comes from a different DAC. So there's another DAC that plays into this, which again also has a divider that can be selected here. And I'm not really sure what source fine's doing. Yeah, I couldn't really say about that. Is there anything else that's kind of missing here? No, I could talk to you about the bits of this that were So some of the bits that blew up on this schematic, this is one of the diode pairs. This is on the top side. So if we have a look, that's this guy down here, the CR104, which I've already rebuilt. CR107, that blew up. So you could see one of the current paths was that on the low side, the voltage came through and then went through like this and killed that. On the other side, the way that we've got some damage to one of the relays, so K1 was damaged. Is that right? No, let me just check. Yes, K2 was damaged, right? So K2 was damaged through this upper path up here. It seems that it was damaged coming up and then through, and then what died was actually a resistor that's here. So weirdly, if we look at the schematic that I have, there was this resistor on the back of the PCB. So I don't think I have that anymore in place, but there was a resistor between this point here and this point here, right? So this kind of additional bodge resistor that's there, and I've named it the mystery resistor, or the Mr. Resistor. And I'm not sure of its value. It was blown up. All I could tell was it had a gold band on it. What do I think that is? Well, you might see resistance in the directly in the output of a op amp if you're worried about driving a capacitive load. And so these resistors are usually some low value, tens of ohms, right? Or 4 ohm, 5 ohm, up to 40 ohm is what I've read on the internet. So if this looks like actually somebody had this op amp directly driving the output originally, but then they've cut this trace and added a 10 ohm resistor to prevent kind of oscillations due to capacitive loads. So I'm a little less worried about this now. I think, oh sorry, it wasn't connected to that terminal. It was connected to that terminal, clearly. It's just actually bodged between the two terminals there, where this trace was originally just a dead short. So what I'm going to do there is I'm probably just going to put a 10 ohm resistor in, and just see how that goes. And if I get oscillations on the source voltage on this, then I'll try upping that resistance. But for now, 10 ohms seems to sort of work. It wasn't a high precision resistor; it was a few percent. So yeah, I don't think it's a critical addition. Just something nice to have. What else can I talk about? Oh yeah, what else blew up? So that resistor blew up, which seems to connect to here. And then actually I lost some of the other resistors on the system. So it looks like the diodes are fine, but this Q105 was dead. So we actually somehow managed to kill that. And at the same time, we also, this R148 was dead as well. So this 27 ohm resistor was dead too. At the same time, so was Q106. So it looks what happened is that there was a current path through this op amp, through its negative rail, down through this diode, through this MOSFET, and then that might have gone either through the gate and killed 106, or it could have gone through 27 and killed that there as well. Then it could have cascaded out everywhere else, but I don't see it. So for example, this U7, I'm fairly sure that this is protected by this 600 kiloohms of resistance that we see here. This diode also seems to be okay, seems to have survived. So everything I can see that's connected to this node, it has extremely high impedance, right? Half a mega ohm of impedance in each direction. So I think we're good. Onto this one. I think this op amp here is dead. You can see that I actually removed it here, so it's gone. I see the reason why I think it's dead is because I see 20 ohms of resistance between its power lines, and so I think something kind of went kablooey there, even though it looks absolutely fine. So I've ordered a replacement one of those 8820s. On the high side, though, everything seems to be okay, right? This transistor seems all right. This MOSFET seems all right. So I think we had a positive voltage, and that we were protected from that by this diode here. But that shorted out here. So I think I had a very high positive voltage on the source high terminal. And so I think I'm going to get away with just replacing this. Beyond that, the main thing I'm worried about is that there's internal traces that are vaporized. I can't see that. Another thing I'm a bit worried about is these precision resistors. I've checked some of the values. These ones seem a little odd. And it also looks like the power supplies for this front op amp are different to the power supplies used over here. So if you have a look at the the schematic that's getting messier and messier, you can see that these op amps are driven with VCC and VSS, and VCC and VSS are the same as these ones here. But that isn't the case. So I am a bit worried that somehow the power planes associated with these lines have become burnt out on an internal layer, and that could be really challenging to diagnose or repair, because I can't clean those internal traces. So this could still be a dead bust, but it was a very interesting, once I put everything together, if it turns out that the power supplies are bad, I might really struggle to repair that. But I think we've gotten everything. So I think I've done all the repairs needed to at least get the voltage source working and the resistance source working. I've replaced this op amp here. Unfortunately, I bought the wrong op amps, so I ended up buying these 8820s, but I bought the MSOP packages, which are these tiny packages here. The actual package I should have used was, I think this, well, I don't know, I think they're SOIC packages. But yeah, I bought MSOP. Look at that difference. So they're a fraction of the size. So what I did was I mounted on the board upside down and then used magnet wire to kind of wire it in. It's a bit ugly, but I couldn't be bothered waiting to reorder that other piece. The only thing that I don't think I've recorded, I've put a 10 ohm resistor here in replacement of that long resistor. I actually kind of welded it in at the break in these tracks. I thought that was neater than actually having a through-hole component just dangling around in the breeze. But yeah, I think that's everything. I don't think there's anything else bad in this signal path. So we should be able to, I hope, source voltages. If we can't source voltages, then I sort of give up. There is still an issue with the source current. I haven't really looked into that, and none of the changes I made down here I don't think they will affect source current. If I want to fix source current, I'm probably going to have to kind of debug this board and possibly the power supply board, because that's where half the source current stuff lies. So I'm trying to debug the current sourcing issue and the current measurement. So these middle two jacks here, circuit diagram says that there's about half the componentries on here and the other half of the componentries over on the power supply assembly. But in this version, I don't think that's the case. I think there's very little on this board. So essentially what I would do is I would put my meter in continuity mode, and then I would kind of pop one end of it in one of the plugs, and then the other end of it I would just start to kind of browse around and look for continuity in. And you can see there's two capacitors up here. That this is the low side and this one is the high side, and that's where I could trace it out to. But then beyond that, it really doesn't look like it goes anywhere on here. And I was using a trick from Mike's electric stuff to try and trace out these traces. And essentially what he said was, if you just make a little kind of wire brush out of some soft, generally quite soft wire, you can actually, and I've just kind of crimped this together in one of those wire terminals, you can actually then just kind of brush around and try and find contacts quite easily. And yeah, of course I can find a contact here, but there's literally nothing anywhere else on this board. In fact, the only place that I could find it was over here, actually, on this connector. And it actually turns out that the bottom three terminals, so this one, and this one, they all connect to the low, whereas the high actually connects to the three terminals up here. So essentially the bottom wires here are actually basically the input jacks after it's come through some filtering and a little bit of capacitive decoupling here as well. Okay, so where does it go over here? Well, if it's on these three pins, it goes onto this side of the board. And if you flip this board over, and I just kind of make some space, what you can see is the one of the traces comes here and then goes on this thick trace all the way up to up here. And what we have here is we have what looks kind of suggestively like a current shunt, right? So this is a 10 ohm current shunt resistor that we'd see here. mainly because, you know, it's labeled as a resistor, but it's just so big. And if it's this big, then usually what it is it's a precision resistor. And so we could see 10R there, and then a little bit north of that, we could actually see another thing that kind of looks a little bit suspicious because it doesn't have a polarity marking. It's not a capacitor or a diode. Again, it's labeled R, so it's resistance, and you can see it's got this plus or minus 1% on there. So it's a 1K plus or minus 1% resistor as well. Now, if anything's broken in this current thing, it's probably these current shunts. And the reason why I think it's probably the current shunt is because it was outputting not 1 volt or 1 amp, 1 milliamp, and it was saying it was reaching its compliance voltage and that it couldn't output any current. And I think it's probably the sense. I think it can't actually see that it's actually outputting current or measure the current that it's outputting. And so I think it's these guys. Now, if I take my meter, so if I have this meter in ohms mode and I try and measure out these things, so this should be 10 ohms from side to side. You can see I actually get 10 mega ohm, and that's pretty worrying. And then if I kind of go across this guy here, I get another 10 mega ohm. So it's looking like these shunts are just blown wide open. If that's the only issue, I think I get off quite lightly here, considering the amount of work I've gone through to get the voltage system working. What I'm going to do is I'm going to desolder these guys and just replace them with through-hole components, cheap ones, and then I'll have to get these on order because I don't have these in stock. If you look at the schematic for the original 701, these are something like 200 or 100 ppm resistors. Now, they don't mean the 1%, they mean the actual temperature coefficient on these. I mean, it doesn't really matter what their absolute value is, you know, 1% isn't that accurate. But what you really want to do is these resistances to remain stable over temperature changes. So I'm going to have to buy some precision, you know, highly temperature stable 1K and 10 ohm resistors to replace them. But if I just want to know if this will work at all. So I'm going to bodge in 2 through-hole resistors just on the top of 1K and then just give the whole thing a try out. Here we go. Try using my fancy tweezers. Let's give these a whirl. Okay, so what I've done, I've just kind of put this thing together. I've attached it to my my meter, and I've got it actually sourcing some milliamps. So I actually just kind of dial 1 milliamp in and hit return. And what you'll see is it complains that the compliance voltage exceeds limits. You can see that this is reporting 35 volts on there, which is what you'd. So all of that makes sense, right? You'd expect that if you sourced 1 milliamp but actually gave it high impedance outputs or inputs, it wouldn't be able to source the 1 milliamp, so it would fail. So if I just put this into the current shunt and actually measure the current, you can see I'm getting actually 7 milliamps, and it's still complaining that the compliance voltage is exceeding the limit. So it looks like it's not just the current shunt that's gone, it's probably a lot more over here. The issue is, but I'm just not motivated. I'll be honest, I kind of want to just see if the voltage sourcing and the resistance sourcing works. And then the current sourcing, I'm not that bothered about just right now. I'd rather move on to some other projects, given this has taken up my bench for like a month and a half, thanks to COVID and everything else. So yeah, fixing those current shunts didn't work. Let's just try out the voltage sourcing. And let's get it all back together as well. Here we go, here's a functionality check with this meter, just showing you how it works. Once it's booted, it actually goes straight into measure mode, measure only. I've got nothing on the terminals there, but we know that that's good. We know that that can measure my SMU pretty precisely. What we're interested in is getting this thing to source. So if I hit source, and then I pick DC volts, and then I put just 1 volt in there, look at what I get. Beautiful. I mean, so nice. Right. We could even just try and just see where the digits stop. Okay, won't let me enter anymore. 1, 2, 4, 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. Ah, I mean, that's so cool. I think the upper limit of this thing is 15 volts. Yeah, 15 volts. So we'll do 14.987. Oh, 14.9876. So we're a tiny, tiny bit off there, you know. Yeah. Wow. We're getting into the microvolts, 600 microvolts. Yeah, we're out about 500 microvolts there. I mean, that'll do for a 25-year-old piece of equipment. That's pretty amazing. Okay, so the only other thing we're going to do here is actually just try a 2-wire measurement. So we're going to do a 2-wire resistance measurement, and we're going to put that in here. So we'll try 10 ohms. Cool, 10 ohms. 10.04. Okay, that's a little bit out, but pretty nice. Let's try a kiloohm. Wow, that's more on the money, isn't it? So that 10 ohms might have been just set off by the fact that this is a 2-wire measurement. I didn't null this. We could actually just put 0 ohms here and just null that for fun. We could be much more precise about this. If we were going to actually try and calibrate this machine, we'd use a 4-wire measurement to the jack. But there you are, 10 ohms now, 9.47. Okay. Yeah, I think this might need a little bit of a cal. But I mean, yeah, you know, I'm complaining about something that is genuinely astonishing. I mean, this is really nice performance for a handheld kind of source resistance system. That is super cool. What else do we have here? Oh, okay, right, we have AC, 1 volt, that's fine, and we'll do that at 10 hertz. Let's try that. So 1 volt amplitude, AC volts. I'm getting half a volt here. Should I be getting half a volt? I'm not entirely sure. Okay, you can see that this thing's on this guy is actually outputting a square wave, which is why we're getting an AC voltage of a half a volt when it's 1 volt. Still, pretty nice. Pretty nice. So I'm not going to try the thermocouple or the RTD, source or measure, because that does require the use of the middle jacks, and I haven't fixed those yet. Maybe another time, but for now, really happy with this. It was a hard repair. There was a lot of work to get this working. Now another cool addition to the bench, at least in terms of monitoring voltages, and then actually pretending to be a resistor or a voltage source. And until next time on that one.